Right. My laptop is doing something crazy. What you are seeing is not what I'm seeing. One more time. Okay, great. Right, so near the surface of Earth, the few lines are uniform. Okay, for those of you who are very sharp with your eyes, you will notice that I was not able to draw the lines equally spaced apart from each other. That was what I meant to draw. It's supposed to be equally spaced apart, but I'm sorry, I didn't take the time to do that. Okay? So they are supposed to be equally spaced apart, they all act downward. Okay? This tells you it's a uniform field. This explains why we use G equals to 9.81 on the surface of Earth. Okay? So now let's get down to the definition. Remember in the summary, I show you F equals to mg, right? In the arrow linking force and field, I give you F equals mg. But the definition of G is F over m, is force per unit mass. So one more time, the gravitational field strength G at a point is defined as the gravitational force per unit mass acting on any mass placed at that point. Or acting on a mass placed at that point. The keywords is force per unit mass, and in this case the force is gravitational force. Okay? Can you add the word gravitational force on your notes, please? Gravitational force per unit mass. Okay? Which is basically this equation. And since the unit is newtons per kg, it's in your notes. And since we know that F equals to G m1 m2 over r squared, we can derive the equation of G to be as such. Yeah, the box is a little bit small. Basically, you only need this part. The box is only for this. The derivation you can copy to the left of the box. Oh, I give you two boxes. Right, sorry, there are two boxes. Yeah, the left box is a bit too small. I should increase that size. Mental note. Let me write that down. Okay? Okay, any questions? So just like force, we sometimes add in a negative sign. Okay, when we don't, we are talking about magnitude. When we add in, we are specific about the direction. Okay, so at A levels, if you give me this, it's fine. But since you are my students, right, I must tell you, when you go to the university level and you are talking about astrophysics with your professors, please have a negative sign. Okay? Know that it's there. Right. Moving on. Example 2. Example 2. We have two masses separated by a distance of 0.25. That means M1 and M2. The distance between them is 0.25. You have a point X, which is 0.2 from the 800 kg and 0.15 from the 600 kg. What is the field strength at point X? So remember, the diagram is not given in the question. It's not. Given this data, you should be able to figure out that X is a point where the two forces act perpendicularly to each other. Are you able to? If you are not able to, can you imagine 25 divided by 5 gives you 5? 20 divided by 5 gives you 4. 50 divided by 3 gives you, divided by 5 gives you 3. And you can see very clearly that the distances 3, 4, 5 must form a Pythagoras, a right-angled triangle. Yeah, have to lah, huh? Physics, you need to do this kind of stuff. Next, they ask you what's the gravitational field. So, because they are not acting in the same direction, you must add them together vectorially. Forces and fields are vectors, so you add them together vectorially. Okay? So the gravitational field at a certain point, due to what is a vectorial sum of the individual vector. So let's find the individual magnitudes first. I've given them to you. It's a simple application of the equation in the boxes. The resultant, I can use Pythagoras theorem to find them. Okay. So draw in the resultant gravitational field in the diagram. The space to the right and the angle is not for this diagram. This diagram goes on to where X is, right, between the two masses. Okay, and there's a little box that I gave you, right? It says that these are perpendicular. That's why I can directly use Pythagoras theorem. If they are not, you have to use what you've learned in vectors to resolve them. Okay, so add in this line of G resultant, and angle theta. The second thing that you need to learn is that it is a vector, there must be an angle. So if you're asked to find the resultant vector, you must find both the magnitude and the direction. Okay, are you done with the diagram already? So, this is what, yeah, by right I should give you some time, but I spent too much on the video. So, yeah. To find the angle theta, you got to use the inverse tangent. Alright? And find the angle theta. Then you describe them together. Okay. Right. Hence, the resultant G field is an angle of 37 degrees to G2. Okay. Do you need to say clockwise from G2? Yes, if you want to be more specific, but we already have a diagram. It's not so bad. If you want to be more specific in your words, you can say resultant gravitational field is of the value of 2.22 10 to the power minus 6 and the angle 37 degrees clockwise from G2. You can say that, not an issue. Right. Next, part B. They then ask you, if a mass of 300 kg is located at X, what will be the force it experiences? So, using the equation F equals to mg, you can find that very easily. Okay? Which also allows me to illustrate this point. If I place a mass of 600 kg, twice of before, the force experienced must be twice as large. Okay, which explains why someone with a mass that's doubled of another will experience twice the weight. Okay, your mass is not a weight. Right, yay. Example 3. Done? Huh? No. No? Is there any? I given you everything, right? Okay, I heard wrongly. Example 3. Example 3 is really cool because, can I ask you, what is the weight of this water bottle? What will you do? With a weighing scale, right? Correct? How do you weigh the earth? Weighing scale lah? No. Unless you are the guy with the glove. No spoilers. If you know, then great. If you don't know, it's okay. So how do you do it? And this has perplexed people, right? Like, oh, how heavy is the earth? And really, it's quite cool. It's because there was some smart guy, a mathematician actually, who actually found out Earth's radius first. Do you know how to find Earth's radius? Take a measuring tape, right? And go around. Obviously not, right? So there was some smart guy who did that first. Then there was a second smart guy who, no, not this one, not so. This one's quite easy. Everyone can do it, right? Who found G to be 9.8. And then they said, oh, then they came Newton and said, okay, if this is true, we can then find the mass of the Earth. And let's try it. So, we have this. We can then easily rearrange M in G R squared over G. Notice the difference in the R. Do you notice the R is different? What's the difference? Conventions are boys and girls. Small r is to denote a variable. You are applying the equation as it is. You're just copying it over. Big R is in the question defined as the radius of the Earth. Oh, we didn't. Well, okay. Can you write down there where R, capital R, is the radius of the Earth? Okay, so we must be very careful. Big M here also represents, if you notice, a specific mass, the mass of the Earth. Okay. If you look back into the equations that I've given you for force, I've used M1, M2 to decide. Yes, I've done that. Right, so next, the rest is just substitution. Right, and you get this. So these are the conventions. R is usually denoted for a variable. R or RE is to denote a fixed value, like that. The Earth. Okay? Oh no. Oh no. Not enough time. Right. The next part, the determination of G by experiment. Example 4 first. Example 4. Sorry, Can? Done? Okay, done. Next part, example 4. Oops. Assuming the Earth is spherical, show that density is given by this. Well, can be done. So let's start. Density is mass over volume. Plug in the M that you found in example 3. Write the equation. Volume of we assume Earth to be spherical, so 4 pi r cubed over 3. Notice that both r's are capital R. You rearrange and you get this answer. Okay. The G's and the R's are specific. Okay, this G here is specific. This G here is specific. Oops. It refers to 9.81. Okay, it's not a variable g that changes as you go further away. Right, speeding up. This part you can read at home because it's your kinematics equation. It is a tutorial question in the supplementary question. The supplementary tutorial question, this is a question. Okay, so moving on. Depth of G and height. So using this equation, we know that we can do this. For a radius of Earth r, capital R, it must be a 1 over r squared graph. Alright? What about G within the Earth? So now, if we use what we have done in example number 4, right, we know that the mass of the Earth, actually we don't need to use it. Okay, don't need. We can just use Gm over r squared to find the mass. So this one, notice the field at this point P, listen carefully, is due to the mass. Let's say at point P, you are radius r, a certain r away, is due to the mass enveloped by that sphere of radius r. Okay, so you only need to consider the mass within it. This shell theorem, don't need to know. But I'm just saying that you need to know that at point P, the G at that point, it's only the mass envelope inside. So if you go within Earth, the mass envelope is less. The G must decrease. If you go to a radius where, at the center of Earth, where no mass is enveloped by an infinitesimally small r, there's no G. That means if I can drill a hole through Earth and I leave you right in the middle, you will stay there. Okay? Which is why some scientists are saying that they want to dig a tunnel through Earth. You can use gravity to power the train, and you will appear out on the other side of the Earth. I think Japan is exploring a deep underground train to use gravitational force to propel the trains to and fro locations. It's very smart, but I'm not sure if they can do it. The engineering is crazy. Okay? So this is what happens. You plug in the values, you sub, you get this, and simplifying, you get this as the answer, which then allows you to say that G is proportional to R within Earth, and allows you to write this. So together, you get this for the graph. Okay, so for your graph that you have drawn on page 6, you have a curve and your straight line down. Okay? Which also means, very cool, theoretical. If I can, you know what's opposite to Singapore? If I drill a hole through Singapore, there is somewhere in the States, right? Around there. If I can do that, and the ocean doesn't flood in, I can literally deliver a package from Singapore to the States by dropping it through that hole. You will fall. I mean, the package being a human being. Then flip the side, and come out on the other side of the Earth. There is a movie, there's a sci-fi movie that has that. Do you know which one? If you go and watch the sci-fi movies in the future, right? There is a scene in one of, I forgot the name, I couldn't find it. If you know, please tell me, I'll put it as a video. They were transported through the Earth, and through a certain point, right, the gravitational field flipped direction. In the middle, they were floating. After that, they flipped direction, and they came out the other side of the planet. There's a sci-fi movie like that. If you see it, please email me the name, I will be grateful. I saw it and then I forgot. I said, this one I must write down and show. I forgot to write down. Okay? Right, sorry. However, this makes certain assumptions. It assumes that Earth is of uniform density. In reality, it's not true. It looks a little bit more like the blue line here, like this. Okay, it is not true. But this one you don't need to know. Okay, just know that it's an assumption. What assumptions are made to that? Homework, go and read example 5. It's very easy. Once you have the equations, just apply it. Okay? Go and read example 5. So the next lesson, we will start on the applications. Okay? Thank you very much. Goodbye.